one more term, very basic term, which we say is a isomorphous system. We have already said that we have been talking about binary systems, which means that they have two components only, like copper and nickel. So it is a binary system phase diagram. If it is isomorphous also, the meaning of the term isomorphous is that at low temperature, I have only a single crystalline solid phase at low temperature. That is what you observed here. If you see that at low temperature, I have only this alpha. There is no beta seen here. So that is why this is a binary isomorphous system. So our isomorphous system says that at low temperature, there is a single crystalline solid. Similarly, at high temperature, there is only a single liquid phase, and there are only two boundaries. Keep it in mind, there are only two boundaries, the liquidus and the solidus. Whereas for your iron carbon system, that may not be true. We will see just today only that what is the difference. Let us see first with the help of another diagram before moving on to the FEC diagram. If I want to move to that diagram, let us see that what will happen to the microstructure, or how does solidification takes place. It is very simply explained here that at point A you have all liquid, at point B the solidification starts. You can see here that at point B, when the solidification has just started, so you can actually then apply the lever rule here. The arm length on the opposite side will be very small, and whole of it will be then liquid only. So when you come to the lower point, you will find that the things change, as we have seen that this is how it keeps on changing. I explained it already that it is observed that during solidification, or I can say here that phase transformation, I define one more term which we call as phase transformation. That is, phase change is happening. Phases are transforming, phase changes are happening. So from liquid phase, you are converting to liquid plus solid phase. And then from liquid plus a solid phase, you are actually going to a single solid phase. So there is a phase transformation happening. Why it is happening? Because you are lowering down the temperature. If you are not lowering down the temperature, the phases are in equilibrium, and that is why these are called as equilibrium phase diagrams. So if you maintain the constant temperature at A, nothing will happen. Liquid will stay. It is in equilibrium here. But when you lower down the temperature, because you change one of the thermodynamic variables, that is the basic reason why the phase changes start, why the phase transformation takes place. And we have already seen that what is happening, that during solidification, the composition, the relative, both things are changing. The relative amount of L and alpha is changing, and the composition of L and alpha is also changing. We have seen it already. Okay, so we have already said that okay, you can find lever rule to find out the relative amount of phases here. This is how you do that. So the point B is the start of solidification, and there at the when it is touching the solidus line, we are saying that is the end of solidification. The solidification is ending. So in between you have something like this, and at the after the solidification has happened, the microstructure will look something like this. So it will be all shown as what we refer to as blue one. So it is all single phase alpha. What is visible here is these are what we call as grain boundaries, because the solidification is not happening at one point. So they're all nucleating separately. You can see that. And once they nucleate, you will find that at this point, when the temperature is lower than the solidus line, you have what we call as only single phase alpha, which is polycrystalline. Okay, but as I said, that this thing is happening just because we are assuming that this cooling is happening at a very slow pace. So we are assuming that the cooling is happening at a very slow pace, and that is why we are seeing here that this change of composition is possible. So what I mean to say, I will just repeat that it has an understanding, it needs an understanding, and I will explain it with this diagram here. I already said that with continuous cooling, both compositions and the relative amount of each of the phases will change. We already know that. So you are at B. So this is how the composition of L and alpha is there at B, and the relative amount of L and alpha at B is also changing. Right now, what we are showing is that the composition of the liquid phase is 35% nickel at point B, and this is 48 or 46% nickel at for alpha. When you go to point C, this is changing. So you go to another one. When you go to point D, you find that you come back to where you started from, around 36 is there. But once you go to the blue line here, you come back to what we started from, that is point E, that is here. So during this solidification, we observe that there is a continuous change in the composition of the liquid and the solid phase, which simply means that atom movement is taking place. Atoms or nickel atoms, if I'm only talking about nickel here, so nickel atoms, here there are 35%, here there are 32% in liquid, means from liquid they have gone into there is a movement taking place. So that movement of nickel atoms which is taking place will be requiring diffusion. It is happening because of diffusion, and it will need some time. And that is why we say that this equilibrium diagrams or phase diagrams are valid only in the case of slow cooling. When you cool them very fast, the time for diffusion is not there, and then you don't observe this. So this is what we need to keep it in mind, that the equilibrium phase diagrams are achieved, the phases in the equilibrium diagram are achieved only when you say the cooling rate happens to be very, very small, or very slow cooling is used there. So when you don't do slow cooling, this is what you observe, that this is traditionally what will be happening when you are having slow cooling. Here, this point, this point, this point. But what happens once you fast cool, that initially what is happening, do that at this point you have alpha which contains 46% nickel. When you go at from this point to the second point, you have a true phase. Now what is happening here, you have a coring phenomena, we call it as a coring phenomena, means the inside the red one is having a different composition, the outer crystal is having a different composition, because I am cooling it fast and I am not allowing it the time for diffusion, so that there can be same composition in the solid. So this will result in what we refer to as coring, or what you observe is that you have something like this, the grains which are not having the same concentration of nickel, but they will have different ones. Initially they started with a higher one, then you start reducing it, then you start reducing it. So you may not land up with this point, but you follow this curve and you may land with this point here. Okay, so this is what the problem there is with the help of what we call as non-equilibrium cooling, and we will see it not in this context, but maybe in the context of iron carbon diagram later, that what is the problem that you have with the coring that is happening because of fast rate of cooling, that what is the problem with that. Okay, yes, now we already said that you go for alloying just to increase the mechanical properties because of solid solution strengthening. So this is what is observed in the case of your copper nickel isomorphous system, where you see here that and I'm plotting tensile strength versus composition in terms of nickel percentage only. We find here that when you start increasing the nickel percentage in copper, the strength of the copper, it was here, let us say it was 100% copper here. It was 100% copper, it is a low strength. So when you start putting nickel into it, it starts increasing here. And it goes to a maximum value, then it starts coming down, because now the reverse thing is happening. So this is what is observed here in the kind of mechanical properties, that improvement in mechanical properties is observed because of what we call as alloying.